slides now?
Yes, perfect.
Okay, so I was asked to give a short summary of different cosmological interpretations of the NANOGrav result. So during the past couple of weeks, I have seen these papers on arXiv which are related to the NANOGrav signal. So they all interpret the signal as a stochastic gravitational background, and then the source can be, well, there is many different sources that can give rise to that kind of signal in cosmology. First one is cosmic strings. Second is scalar-induced gravitational waves related to formation of primary black holes. Third one is gravitational waves from first-order phase transitions. And last one is primordial gravitational waves formed during inflation. So in the following, I will briefly show you the results of these different studies. So I'll try to summarize them. But before that, I will just show you the feat that was already seen in the previous talk. So what they observe is a narrow frequency range, and they provide a feat which is a power law in this narrow frequency range. The orange contours here, they show the feat to the 5 lowest frequency beams, which are kind of most clear, as we just saw in the previous talk. And so here A is the amplitude of the gravitational wave strain, and gamma is a power. So G minus gamma over 2 is the power of the gravitational wave strain. So now if we convert this into a plane where we have the gravitational wave abundance at 5.5 nanohertz, which is in the middle of this frequency range, then we see that the abundance is around 10 to the minus 9, and the power of the gravitational wave spectrum omega is 5 minus gamma, which is around 0. Oh, it's not very steep. And in this panel, this plot, well, you can see that PTAs indeed probe very low frequencies. The signal is somewhere around here. And then in the following, we will see some example where this signal can be observed also in other experiments in future. Possibly. So first interpretation is that maybe this signal is from cosmic strings. Cosmic strings can be formed in the early universe in breaking of some U1 symmetry. And then these strings, they form loops, which decay through gravitational wave emission. And the gravitational wave spectrum that you get from cosmic strings is determined by the string tension G mu. So in this paper, I took this plot from this paper by John Ellis and Marek Levitsky, where they studied this possibility. The solid and dust contours show the 1 sigma and 2 sigma regions of the NANOGrav feat. And this rainbow line here shows what you get from cosmic strings for different values of the string tension. So what you see is, for example, that if G mu is around 10 to the minus 10, you get the signal which is within the 1 sigma region of the NANOGrav feat. Then in this plot, if you show that, so here around nanohertz frequencies, the NANOGrav observation fixes the string tension, and that fixes the gravitational wave signal that you get from the cosmic strings. The signal is shown by these black lines. The signal is almost flat across very wide frequency range, so a nice feature of this interpretation that the signal is from cosmic strings is that you can probe this with many future gravitational experiments. The second interpretation is related to formation of primordial black holes. So the standard scenario of how brown black holes can be formed is based on having high peaks in the curvature power spectrum formed during inflation. So this is one example of a curvature power spectrum that has a high peak at small mass scales. CMB is somewhere around here, and the amplitude of the curvature power spectrum there is very small. But at much smaller scales, you can have a high peak in the curvature power spectrum. So when these scales corresponding to this peak, when they re-enter the horizon after inflation, they can collapse and form black holes. So this plot here shows the mass function that you get from this kind of peak in the curvature power spectrum. The mass of the black holes that you form is roughly given by the horizon mass at the time when these scales re-enter the horizon. And the black hole abundance is very sensitive to the amplitude of this curvature power spectrum peak. Basically, it's exponentially sensitive to that. And then there is actually quite large theoretical uncertainties in the calculation of the abundance. This kind of peak in the curvature power spectrum leads also to formation of gravitational waves. So large scale of perturbations, they source tens of perturbations at second order. So this peak curvature power spectrum transforms into a peak in a stochastic gravitational wave background. The position of the peak is given directly by the wave number at which you have a peak in the curvature power spectrum, and the amplitude is simply proportional to the curvature power spectrum amplitude squared. So now, if you want to fit the NANOGrav result with this gravitational wave spectrum that you get, first of all, if you have a narrow peak in the curvature power spectrum, then the tails of the gravitational wave spectrum are too steep to fit the NANOGrav result. So the peak of the spectrum has to be around the NANOGrav scales. So now, looking close to the peak, you get different values for the slope at the frequencies that the NANOGrav observes by fixing the position of the peak, and the amplitude of the curvature power spectrum, it fixes the gravitational wave amplitude. So here now, the solid and dashed contours show the NANOGrav fit, and in the same parallel you see the brown black hole abundance that you form for the corresponding brown black hole abundance. Here FBBH is the fraction of dark matter in brown black holes, and what you see is that, for example, within the 1 sigma region, the brown black hole abundance is very small. It's less than 10 to minus 12 fraction of dark matter abundance. Instead, if you have a curved power spectrum that has a very shallow high K tail, then it means that also the gravitational wave spectrum that is induced has a high K tail, which is not very steep, and therefore it can fit the NANOGrav observation. So now if the NANOGrav sees something from the tail, then the peak is at higher mass scales, so you produce heavier black holes, and kind of quite interesting part of the parameter space is where you can actually produce seeds or supermassive black holes. So here now from the tail, the slope of the gravitational wave spectrum is fixed. It's proportional to f to the power minus 1. These, now in this plot, the NANOGrav range is just the range in omega. And then by varying the position of the peak in the Kurzweil spectrum, you get different peak mass for the crowded black hole abundance. So indeed, the region where you can produce seeds for supermassive black holes is within 2 sigma region. Another scenario was presented in this paper. In this case, the Kurzweil spectrum is like a theta function, have a very long flat peak, the Kurzweil spectrum. So what this then means that the gravitational wave spectrum that you produce is also flat across very many orders of magnitude in frequency. And if you fix the end of the theta function, you can, well, by fixing the end of the theta function, you can realize a scenario where all dark matter is in brownish black holes of mass below 10 to minus 12 solar mass, and you fit the NANOGrav result. Okay, then the next possibility that was considered is that maybe this signal is from a cosmological phase transition. So from first order phase transition, you get the gravitational wave spectrum that is a broken power law. The low frequency tail of the spectrum is proportional to f to the power 3, and therefore it doesn't fit the NANOGrav signal. It's too steep. So if you try to then fit the peak of the spectrum to the NANOGrav result, the peak frequency is given by this expression. And if the peak frequency is around 5.5 nanohertz, then you see that the temperature at which the phase transition happens should be about 50 MeV divided by beta over h. Where beta over h is, well, it gives the rate at which bubbles nucleate in this phase transition. Now, okay, so the temperature, okay, beta over h is typically, let's say, larger than 10. So the temperature is very low. This means that there is constraints on these kind of phase transitions from big bang nucleosynthesis. There is 2 ways to avoid these constraints. One is that well, let's say that the phase transition happens in some hidden sector, then the energy should be transferred to radiation before big bang nucleosynthesis. Or if this sector where the phase transition happens is completely decoupled, then there's constraints on the energy density in that hidden sector. So because the energy density in the hidden sector basically changes the effective number of neutrinos. So in this paper, this NANOGrav signal was interpreted as a signal from a phase transition, and it was pointed out that well, if you have this kind of dark sector where the phase transition happens, then the change in effective is related to the strength of the gravitational wave signal, as is shown in this left panel. And then with the if the change is around 0.4, then you can alleviate the Hubble tension. So there's a nice possible relation there. And finally, today there was a paper about inflation. So during inflation, you produce tensor perturbations. And in order to explain the NANOGrav result with these gravitational waves from inflation, you need extremely blue tensor spectrum. and this actually is in tension with ppm constraints. So here nt is the tilt of the tensor perturbation spectrum, and r is the tensor to scalar ratio. The blue region is the projected NANOGrav detection, and the region right from the dashed line is excluded by ppm. So indeed, this doesn't work. Okay, so I think I'm already out of my time. I just leave it here.
Thank you. Questions?
Can I have a question?
Sure.
Yeah, can I take a look at your power spectrum of the scalar perturbation, which has a Gaussian form, like or log normal, in the first example you talked about in your paper?
All right.
First
this
example.
Yes.
Yes, this one. Yeah, I would like to know that you said in your paper, you said you choose some parameters like the width of the peak. So I would like to know why you choose that the width, because according to my understanding, that if you have broader peak width, then the power around the peak will be much a little bit smaller. Then you can feed the data much better, right?
Yes, yes. So indeed, so we fixed the parameters of this spectrum.
Yeah, you fixed the width to be like, according to my estimation, 0.6 or something like that.
Yes,
but you make it a little bit larger.
So it was motivated by a double two-field inflation model, where you actually get a spectrum like this. Maybe you can consider some different model where you get a different kind of spectrum, and then indeed it may change the result a little bit. But I would expect, because basically the observed signal is kind of small. I mean, I wouldn't expect that you get much different from the black hole abundance by changing the width. It will, well, yeah, it will basically change the masses of primary black holes that you get, because then you can take a little bit smaller or a little bit bigger k-star. But it will not
because I thought if you have a broader peak, then this around the peak it becomes flatter, and it fits the range of the power much better, right?
Yes.
I just wonder why you consider a broader peak.
Well, yeah, this was just motivated by a two-field inflation model.
I see. Okay, thank you.
So there is a question in the chat from Sam Young. How was the abundance of primordial black holes calculated from the scalar power spectrum? There have been several different methods proposed recently.
Yes, so well, unfortunately, I don't have the details here, but what we did, so actually there will be a updated version of our paper tomorrow. We studied this a little bit in more detail, but the main conclusions don't change. So what we did for the black hole abundance calculation, well, it's kind of difficult to explain just this. This is choice of window function when you translate the from the curvature of spectrum to the variance sigma here. The window function that we used is a real space top hat window function, and then we have a transfer function, and we take into account non-linearities in the relation between the matter perturbations and the curvature perturbations. So I think it's, well, I think we did the best we could.
I think that the main point is which kind of statistics did you assume? Is it Gaussian or non-Gaussian?
Oh, right. So we assumed that the Gaussian power spectrum statistic is Gaussian.
Okay. Other questions? I have a related comment or curiosity about the other model, the one in which you get 100% of dark matter, this one. So you need a theta function power spectrum. So I understand, but do you know a model in which you can get such a flat power spectrum? And if yes, what is the physics that you need?
Right. So there was a reference to some model in this paper, but I don't know the details about that.
Okay, look at the paper. So other questions for Ville or Alberto?
I have a question actually for also maybe more for Alberto, and this is related to the to the dispersion measurement that he mentioned, and I wanted to know if he had more clues about that. I mean, usually what you do is that you measure, for example, the density of the interstellar medium